to have Eric Vanden-Eijnden as our speaker. Eric is a professor of mathematics at NYU Colloquium Institute, and Eric's research is focused on mathematical and computational aspects of statistical mechanics with many application areas in molecular dynamics, in neural networks, Earth systems, and fluid dynamics. For those research, Eric has received many prestigious awards, including the German Dahlquist Prize from SIAM and the J.D. Crawford Prize from SIAM. But more recently, I think Eric has become interested in machine learning, in particular generative models and diffusions, which is what I think he's going to tell us in the talk today. So please join me in welcoming Eric.
Thank you. Thank you very much for coming. Thank you for the invitation. It's a pleasure to be here. It's my first time in Seattle. Very beautiful, the campus. Okay, so the mic is working? Okay. So I would like to discuss some advances that have arisen in generative modeling with flow and diffusion in this talk. And the work that I'm going to be presenting was made in collaboration with many people that were either colleagues or postdocs or students at the Curran Institute, either in math or in computer science. And this was started with Michael Albergo, who was a student, he's now moved to Harvard, and Nick Boffey, who was a postdoc, who moved to CMU. And I'm not going to list all the other, but they all contributed, and you will see their name over during the talk. Okay, so I think I don't need to tell you that in recent years there have been enormous progress in unsupervised learning using generative models. You probably by now have all played a little bit with these image generator that you have available on the internet, like DALL-E or Diffusion 3, Stable Diffusion, GenFlow just came, etc., etc. Okay, and these pictures here are fake pictures. So they are just generated as you can do nowadays, which is that you put a prompt, and well, you can guess what the prompt here was, and then you get a picture that is consistent with the prompt, and you can do it several times. You get different pictures until you get one that you want. Okay, and so what I want to do today is to try to explain to you that what are the mathematical underpinning behind these models, and what do they do, and how come that they are working so well. You're not going to get all the answer about the last question because there's many mystery with neural network, but I'll try to explain that as we go along. Okay, so the first thing that was realized that there is a way to phrase this question as a problem in density estimation. Namely, the question is like this: given some data that come from a probability distribution, you'd like to do two things. One is to get an estimate of this probability distribution, and second, to be able to sample it so that you get new data. Okay, so let me try to explain this so that we get the basis, as much as we can. So, what is the data if you do images like this? That you can imagine that. So, think about these images as made of pixels. And for every pixel on the image, you have some channels that contain numbers that tell you how much red, blue, like the RGB color that you need to put, the intensity, and so on and so forth. Okay, so you can transform any one of these images into a vector, right? That is a very long vector in very high dimensions. If it's 512 by 512 pixels, it's 512 by 512 times the number of channels that you have per pixel. And now you think about this as one data point xi. And then the data set is all the image that you can gather, okay, for your training set. For example, this was trained on a data set that is called Celeb A that contain pictures, photographs of celebrities. Okay? And then you're making this assumption in this context, we will see other example later where it's not an assumption, but here you're making the assumption that there is a probability distribution of images that you don't know, but you have sample from it, which are all the images that you have gathered from the internet. Okay? And then if you manage to learn what this probability distribution is, and maybe more importantly, you manage to find a way to sample it, then you can create new data, meaning new images. Okay? And if all goes well, you're going to get image that looks like image and look like celebrities like these, which are not real celebrities. Okay? Okay, so that's what we're going to do today, and we're going to focus on one specific classes of the generative model that they've really, made a big impact. They are the reason why this model works so well. And these are models which are based on flows and diffusion, from my title. And here the idea is that what you're going to try to learn is an ODE or an SDE with the property that you adjust the drift and the volatility in this equation in such a way that if you draw a sample from a simple Bayes distribution, think noise, like a Gaussian, then if you take that as an initial condition for in this equation and you solve the equation in time up to a fixed time, say time t equal 1 that you decide in advance, then this will push sample from this Bayes into sample from the target. Okay? And this little movie is kind of explaining, in picture what's happening. The noise is just choosing all the channel of all the pixel randomly, and so you get just this white noise, which is here. And then in this specific case, a velocity field has been learned that pushes this noise into new samples of flowers, because this has been trained on a flower data set. Okay? And of course, if you manage to do that, well, it's ideal or well suited for generative modeling or for assembling, because drawing noise is easy. You can do that. Solving this ODE, SDE is also sort of easy because we have many tools to do that, good integrators for ODEs, Runge-Kutta, etc. So you can, do that efficiently. And if you do that, you get a sample from U1. Okay? And there are many mathematical results that guarantee that for broad class of distribution, target distribution mu1, velocity field that allows you to push a noise toward this distribution exists. Okay? They don't necessarily need, there's a big part that is optimal transport that does that. We don't need to have optimality here. We just need to have a velocity field that achieves the task. But of course, these existence results from mathematics are not necessarily useful in practice, because what we would want to do here is to find a velocity field and a velocity and volatility that actually do the job. So you need to be able to estimate them in practice, okay, from the data. And the way we're going to do that is using machine learning, and that requires that we have a tractable variational formulation, because what we would like to do is we would like to write down an objective function, which in the parlance of machine learning is called the loss, okay, which you can estimate on the data, and it's a measure of how good your velocity field will do. And then the velocity field, you can represent it by a neural network sufficiently expressive, and then you can use the toolbox of machine learning to adjust the parameter in this neural network until you get the velocity that works well. Okay? And for most of the talk, we will work in suspension of disbelief, meaning I will essentially explain to you how to get this variational formulation, but I'm not going to go into one important detail, namely that we're going to assume that the neural network that we have at your disposal have enough expressivity to actually learn this velocity field. Okay, I'll get to that at the end a little bit, why we think that's possible, but you need to realize, and I want to insist on that this x here, it lives in the same dimension of your data. So it's something which is very high dimensional. We are talking about a motion here, like it was on the movie before, that's moving a point in this extremely large dimensional space that you need to parameterize an image. Okay? So this is a very complicated function that we are trying to learn. Okay. Now, it's possible to do. At least heuristically we know, because there was a very big advance not so long ago. In fact, this is a paper, the paper I'm talking about here was in 2021, so it's only 4 years ago that this emerged, where Song and Ehrman, following other using results that had been published before, proposed a method to do this. And the method that they proposed was the following. They say, okay, suppose that you have a data point, in this case this dog, right? You can pass it through an SDE, for example, think an Ornstein-Beck process that will turn this guy into noise. This is the noising process. And then what they realized is that if you go in this direction, you can try to time reverse this SDE in such a way that instead of going from data to noise, you can go from noise to data. And if you use tools from stochastic calculus, there is a simple way to do that, but with one big caveat is that you can write down this time reverse SDE, but compared to the one that you start from where all the coefficients are known, you decide what they're going to be. In this one, you need now to use an additional term in the drift, and this guy is called the score function. It's the gradient of the log of the probability measure of the sample as they're getting noised. Okay? So it's again a probability distribution in a very high dimensional space. Right? But if somehow you can learn this guy, then, well, you can go in reverse and turn noise into data. And the big advance that they really made is to realize that you can learn this via a regression problem. Meaning you can use the data, which is not only this, but all the data that you have when you you noise this, and you do that for all the images in your data set. You can use this data to actually learn this score. Okay? And I wanted to explain to you how this is done, but I'm going to do that in a framework which is slightly different from the original diffusion model that I think at the end is simpler. And the reason why I want to do that is because if you proceed this way, that limits the choice of the base density because you always turn something into noise, and I'd like to do maybe something which is different. We would like to, for example, turn dogs into another animal or into flowers and being able to go back and forth. And also, I'd like to do that in finite time, right? To not have to push this all to infinity, that's a technical detail. We're going to look at that later. So I'm going to try to explain to you, how this works and why is it a regression problem. Okay?
Can I ask just a quick clarifying one? Is it easy to figure out the F and G that do the noising?
Yes. So, for example, one way is that you take f to be minus x and you take g to be 1. Because then this is the Ornstein-Beck process. Yeah. And the Ornstein-Beck process has this property that if you pass anything through it, this invariant measure is just a Gaussian and n01. So that's what they did originally. Cool. Okay? And I should write that differently, but this is the blog, this is from Song paper, so you use this f and g. But think about f as being minus x and g as being 1. Right? But this guy is, of course, much more complicated and known. Okay. So what I'm going to describe now is this framework of stochastic interpolant, which goes also by the name of flow matching and rectified flow. And this framework is what is now at the core, for example, of stable diffusion tree, or movie gen, which is the last instance of the movie generator and image generator that has been now put forward by Meta in the last couple of days. Okay, and you'll see it's actually fairly simple. So what we're going to introduce, and you know, this was introduced, what I'm going to discuss with Michael Albergo, and there are these two other papers here that were published at the same time, same issue of iClear, which has rectified flow and the flow matching. Okay, and the terminology flow matching is somewhat catched up. So, right, so what we're going to do is we're going to create a process which is an interpolation in sample space. Okay, and the way we do that is by constructing a time-dependent function, which is, this is the simplest instance here, where what you take is, as input here, there is a point from, you know, a Bayes distribution, a point from a target distribution, a Gaussian, which is a latent variable whose role will become clear in a minute, but for the moment you can ignore it. And then they are multiplied, there's a linear combination here with function that depends on time. And these functions are adjusted in such a way that if you evaluate this guy at time t equals 0, it gives x0. And if you evaluate at t equals 1, it gives x1. And in between, it gives something that interpolates between this pair of x0 and x1 that you have chosen. Okay? For example, think about alpha t to be 1 minus t and beta to be t, and forget about the gamma for a minute. You could take it to be equal to 0. Right? So clearly then, you go from, you know, from a sample here, right? You have by definition that I of 0 is x0 and I of 1 is x1. Okay? And what you do is that what you take here is that you take samples, right? You define how you're going to take these guys. For instance, you take them independently from the two distributions. Okay? I have a little picture that explains what this does. Suppose that you have one distribution here is this two moons, and then the other one is the checkerboard, right? Imagine that I draw sample from each of them, and then I pair them in a random way, okay? And then I pass them through this interpolant. This is what it happens. So there's this cloud of point, no move, in a way which is kind of time continuous, like, you know, continuously from being samples on x1, mu1 to sample on mu0. And this explains that you can do that with any two distribution. Okay? And so what we would like to understand is what is this motion and how can I represent it with a flow or diffusion. So before I go further, notice that this is not a diffusion. It's a very simple process that has been introduced here. The Bayes distribution doesn't need to be noise. You can go from the flower to the checkerboard, or you can go from a flower to another flower. You could go from one distribution to itself, right? And maybe, and I will discuss all of these things later, you can also get that you can correlate the data and the, you know, on both ends. Okay, that's one thing. And then, you know, you can do that in many different ways, and I'll explain why it's useful to do it in many different ways, which is that by choosing these coefficients alpha and beta, you can get different type of interpolation. So for example, this is an interpolation without this latent variable. This is something where you put a little bit of noise in the middle. This is something where you dissolve everything into noise, and then you get the flower on the other side. Okay. Now, there's a simple result that you can show, namely that the law of this interpolant at any given time is the same as the law of the solution of an ODE with a drift that is given by a conditional expectation of the time derivative of the interpolant conditional on the point that where you want to evaluate it. There's a I have one proof in this talk, and here it is. So if this, this chain rule, imagine that this is the time-dependent distribution of the interpolant, which you don't necessarily know. And imagine that phi is a test function. Then by definition, the expectation with respect to this measure is just the expectation of the test function over the interpolant. Take d over dt on both sides, then re-express that as the time derivative of the measure, and then on the other side, just express this expectation as using the Taylor property of the expectation as the conditional expectation times the expectation, and that defines your B. So now you have a velocity field. Okay? And interestingly, because it's a conditional expectation, it can be, you can use this L2 formulation, which is that this is the argmin, this guy, is the argmin of all possible b's that you can put in this objective where not the expectation is unconditional. So it's something that you can evaluate very easily, because if you give yourself a test function b, you just need to evaluate over the interpolant, which you know how to do. That's just like the little picture that I said before. So you can evaluate this loss easily. I'll get to why that's important in a minute. Okay, so let me try to show you with a picture. So if you learn this, you're in business, because if you have this probability flow ODE, no, you don't need anymore to have a sample on both ends to construct the I or T, the interpolant. You can simply draw sample at one end and then push them through this velocity field with the velocity that you have learned to get sample at the other end. Okay? And so this is what's expressed here. You know, this actually is from actual data. If you have a Gaussian that you push into a multimodal Gaussian, so a Gaussian mixture with 3 modes, and you do this process and you learn the B, then these are the flow lines that you get, you know, that are the solution of this equation for differentiation. So if you take this and then you push it, you know, it will flow, it will go there. And if you do that for all samples that are here, you're going to get sample at the other end that are from the Gaussian mixture. Okay? So far, so good. Now, why is this, you know, what's called a tractable formulation for machine learning? Is because, as I explained, this objective here, this is LB, this objective, you can evaluate it on the data. Because if you have data from mu0 and mu1, you have data from IT, because IT is just, you know, this guy. The only thing that is random here is x0. So pick an x0, pick an x1, pick a t, you have a value of IT. So you can estimate that, and you can keep drawing x0s and x1 and t's, so that you can estimate this expectation here empirically. That means you can estimate the loss. Yes?
That expectation is an integral on t as well.
If you want to learn it globally in t, you would integrate it. But you could learn it at any given time. So I wrote a simplified formula. In practice, we do it, right? And then, so you can estimate this objective empirically using samples. And then, you know, the magic here is that you can now approximate this velocity field that you're trying to learn by a big neural network, a deep neural network that has many parameters. And then what you do is that you just adjust the parameters using, you know, with the toolbox of machine learning, namely by learning it by stochastic gradient descent. And that gives you the velocity field, or you learn it on the data.
Does this depend on which x0s and x1s are paired in the sample distribution?
So the velocity field that you get depends on the statistics of I, the interpolant, and the statistics depends on whether you choose to couple x0 and x1. In the first example I will show you, the coupling is random. You pair everybody to everybody, but then I will show you example where you can do things that where the pairing matter, if you bear with me for a second. Okay? Okay, so that's, you know, one thing. And this is called probability flow ODE. Now, there is something else that you can do, and maybe I should, you know, go quicker on this, is that I want to relate to what's happening with this score, which is that you can use Stein identity, which actually there is an estimate, that's why there is this latent variable that is added, that allows you to calculate the score, which is the grain of the log of this probability density, right? You can also learn it variationally. Okay, and here is the objective that you have, right? Where again, everything is expressed in terms of IT. So why do you want to do that? It's because there is this little identity where the first time you see it, it really looks like magic. It's trivial in a way, but it's kind of interesting, which is that you can use that the divergence of the score times mu is a Laplacian of mu. just take the derivative, it's just taking that the derivative of the log of mu is the derivative of mu over mu. You multiply it by mu, so you get the derivative of mu, and so you get this identity. Now, why is this identity useful? It's because if you learn the score, right, okay, you can turn this transport equation, that is the first one that we wrote, into either diffusion or anti-diffusion, going backward in time, where what you do simply is that you can add a diffusion term on the right-hand side and compensate it by adding in the drift this term, which means that at the end, these two equations, if you have the exact score, are identical. Okay? There's just the same thing. You're just pushing the measure using, you could always cancel term here and here in such a way that you get back to this. However, if you think about this as stochastic processes, the way to realize the process associated with these equations is different. And in particular, if you use the first one, you get back to the probability flow ODE, where you have an ODE that goes back and forth between these two measures. But if you use the SDE, if you use the other formulation, you get an SDE, and that one allows you, with an amount of noise that you can control, to go from there to there. The law, and that's if you go backward in time, the law of all these processes is the same at any given time, but they are very different processes. And I'll explain to you in a minute why they matter, why this flexibility matters. Let me try to make a little, and the diffusion coefficient here, you can adjust it post-training. You first train your velocity field, you train your score, and then you can use it in different ways. Let me explain, what and we'll get to concrete example in a minute. So, suppose that you want to go from this Gaussian mixture, and I'm going to have higher dimensional example for you in a minute, but this is just to make pretty pictures. Suppose you want to go from this, Gaussian mixture to this Gaussian mixture. You can choose the way you do the interpolation, and you choose the coefficient alpha t, beta t, and gamma t in such a way that, for example, the distribution is being changed this way, or that way, or that way. These are three, if you wish, connection or path in measure space that you have built by different choice of interpolant. And then for each of them, you can learn the score and the velocity field, and now you can try to look at what the process does. If you look at the level of process, what do they do? And for example, if you look at this path, this is what's happening. If you either sample it with the ODE or with the SDE with different levels of noise. Okay, and that's the same for the other connection that you have down there. So you have many knobs that you can play with here. Is how you build the connection in measure space, and then how you sample it, and they are completely separated. Okay, and here you construct map, and these are random maps, right? This is what happened, for example, with the flowers. This is if you pick the same noise here. This guy is always the same noise, and then you put it either through the ODE. You get this flower, and if you were to repeat the process, you'd always get this flower. But then if you push this noise, this kind of draw from mu0 into the SDE twice at the same noise, or twice with different level of noise, each time you do it, you get a new fake flower. Okay, and the viability that you have depend on the level of noise that you put, but of course you can get all possible flower if you take different draws. Okay, and this is done by using simple units to represent the velocity field, so not something which is that fancy. I'll go to more fancy example in a minute. Okay, and there's many of these things that are a bit magic with this neural network, which is that you really get a new flower. So this flower, for example, that has been generated here is, I don't know, it's one of those. You can a posteriori ask yourself, well, okay, you have learned flowers, but maybe you have just learned the data set, memorized the data set. So you can actually look in the data set which one are in the data set that you use for training, which one are the flowers that are the closest to this one. This requires specifying the metric, so it's a little bit of a tricky business to do it. But these are the closest flower to this one, and you see that this one is neither one of them. It has features of all of them, a little bit, but it's a new flower. So it has kind of somehow learn something about the distribution of flowers that you don't know, which is somewhat remarkable. Okay? Okay. I don't want to go too much into technicalities, but the reason why you may want to play with this noise in the equation is that it allows you to control the likelihood. In other words, you can prove bounds, and I don't want to go too much into detail. We can discuss that offline later or by email. But you can actually show that the loss that you're using to learn the drift and the score, the error that you make there has an impact on, so the estimation error that you do has an impact on the generation error. And you can adjust your diffusion coefficient to minimize the impact of this estimation error. Okay? And this is with these bounds, and it's actually fairly simple. It's a proof of Gizanov, and you can actually show that in practice, meaning you can, verify that indeed there is an optimal noise that minimizes this error, here measured in terms of KL, right, which says that you should do the generation with this level of noise. And here it's just a constant level of noise, but more generally it would be a function of time, okay, and verify it. Okay? Okay. So, let me briefly make the connection with this, right? So, what is, okay, so what I'm going to show you, and this is by no means meant to take any credit out of what this guy did, because they were really the first and it was a breakthrough. But I want to show you that this can be rephrased in the context of interpolant. So the math is fairly easy. So let's explain that. Suppose you take the O2 process that I have written here in an artificial time tau, which we'll change that in a minute. So if you look at this SDE and you take data from, here time will be inverse for a while. You take, this is the data here from your target, and then you pass them to this SDE. You can actually solve this SDE very easily because it's a linear SDE, and in fact you know that the law of this guy is just given by this. This is the way it's very easy to get data from this X tau along this, because what it is just the actual data that you have exponentially faded out and that you have replaced by noise with something that also increases exponentially towards level 1. Right? That's what this does. Okay? Now notice that, and so what they were doing is doing that and then learning it going backward. But notice that wait a minute, this I've already said, sorry. Notice that if you change the time here and you say introduce a new time which is e to the minus this tau, what you end up having here is an interpolant. So this guy in low is the same as this interpolant that now goes exactly between 0 and 1 into noise at 0 and data at time x equal 1. Okay? And so once you have realized this, you realize that you have just built a connection using this diffusion. But now you can learn the velocity field and the score associated with this interpolant, and now you can sample it the way you want. You don't need to do the reverse diffusion as they were doing. You can do whatever. Like you can adjust in particular the noise to minimize the impact of the estimation error. Okay? And so conceptually, what has happened here is that this score-based diffusion modeling, which, as I say, was a real breakthrough, mixes somehow conceptually two operations, which is building a time-dependent measure, which is what you do with this noising process, and then sampling it, which is learning the B and the score that allow you to go backward or forward and backward. Okay? And when you think about it from the viewpoint of stochastic interpolant or flow matching, you realize that these two things are separate and you can perform them independently with many different ways to do the sampling. Okay? I will skip this slide. There's another tool that is being used in practice, which is that you can use what's called denoiser. Okay? There's a connection with denoiser. So it's a continuous time version of what denoiser do, and as a result it removes the drift, but I want to skip this and give you focus maybe on some application. Okay? So first of all, and this is a bit like propaganda, so forgive me for it, but you can actually scale these things up And since this was done, diffusion tree has appeared, and then, you know, this movie gen, so I should really remove that, but that's what we did, okay? And in fact, so these images are fake. And this is applying, you know, you can apply this on ImageNet 512, like full resolution. And if you use transformer architecture, which is, you know, the baby of my colleague Seining Cheng, which is to use them, is called diffusion transformer. You can adapt them to do the calculation here, and you can get what's called state-of-the-art image generated. All these images are fake. The only part maybe that is worthwhile mentioning is that, and I'll get back to that again at the end, is that to get images like this, you need to have neural network in which there is about 700 million parameters, and you need to train them for 7 million epochs. Okay, so it's kind of pretty heavy calculation that you need to do. But once you have done it, you have your interpolant, and now you have your velocity field, and you can generate these images. Okay. Let me maybe explain a little bit why you can do things that at the end you can do everything with diffusion by rephrasing it, but let me show you that you can do it here quite directly, right? We discussed at the beginning that we can couple the data on one hand and the other, and that we can now go from a distribution, any distribution, to any distribution. So here's a problem where this comes handy. The task at hand is the following one, is that suppose that you have a training set in which you have clean images, full resolution, and then you have low resolution noisy image. And the task that you would want to do is to build a generative model that takes a noisy image and give you a clean image. So clearly, if you want to do this, it sounds silly to turn this into noise, and this information should be put somewhere into the mix. And also, it sounds silly to take your data set of clean images and to not pair the clean image to its low resolution version. So there is a very natural coupling here that you have between x0 and x1, right, that come directly from the training set. So you can actually do that. And if you do that, well, these images here are not from the training set. They are from a test set where after training you take this low resolution image, and I don't think it shows very well, but you can get high resolution image that are close to the one that were in the data set. Okay, of course it's a probabilistic inference here. So what you get is a sample from the distribution of high resolution image that are conditional on this resolution. There's many of them in principle. Okay? Here's another task of the same type. It's in painting. So here the data set that you have are images with masks. And the mask can be put at random location. Okay? And the task is that if I give you an image with the mask and you know where the masks are, you need to in-paint the masks to get the full image. And so what here is the same. Clearly you want to train by coupling the masked image with the unmasked image in your training data sets, if you have them. And then you just learn a velocity field that will do the in-painting. Okay? And when you do that, you can condition on the fact that you know where the masks are, so the velocity field should not do anything. You should not change anything in the image if you are outside of the mask. But in the mask, you should do something. And this is non-trivial because you don't know a priori where the mask will be. This information is given to you, but in the training, there's many different arrangements of the masking. Okay? And as you can see, this is again what you get at testing stage. These models do remarkably well in the sense that it is not putting, when you give it this, the image of this leopard or this image of this bridge, is not putting, a sail in the middle of it. It's actually putting something that is consistent with the image and that one too. Okay? Okay. So far. So now I want to, maybe give you, I'm going to skip this because I'm going to go later into that. I'm going to go, or maybe not. Do I have time? I have time. Maybe I can. So I want to use that. I want to go a little bit more now into applications that are more from scientific computing, where there is a model that you can use. So one is that we're going to take Navier-Stokes equation, in 2D. I've written it in vorticity formulation. And then what we're going to do is a task where if you have a long time series of this, the solution of this equation, it's invariant measure, and we are working in a setup where it's a turbulent flow, but it's in stationary. It keeps moving, but there's nothing. It's an invariant measure. What we want to do is that you want to give a full, you want to give an omega t, so vorticity field, and then you want to forecast the vorticity field at later time, and you want to possibly do that if you give something which is a low resolution vorticity field and get the full resolution. This problem is not very different conceptually from the problem that I showed you before, which is that it's a conditional generation where you give a sample and you want to get a conditional sample based on the pairs that you have in the data set. And this works in the sense that you can give vorticity field and predict forecasts, probabilistic forecasts. These are probabilistic forecasts of possible velocity field that would evolve from this one from the Navier-Stokes equation. Okay? This problem has one feature that makes it a little bit more amenable to benchmarking than images, is that I know, or we know, that this is supposed to be solution of the Navier-Stokes equation, so we can actually test how good these are solution of Navier-Stokes. And in particular, the one thing you can do is that you know what is the entropy spectrum, is how much there is entropy, if you wish, or think energy, but it's for the vorticity in terms of wave number. And so you know it from the data, and you can check that your generative model is actually consistent with that, meaning that it's not only doing things that looks like nice image of the solution of Navier-Stokes, but in fact they have the features of the solution because they have the right entropy spectrum.
Can I ask about that? So
yeah.
Is the spectrum, are you giving that knowledge anywhere in there?
No.
But you could potentially, even if
Yes,
you
that's a very good point. You could use,
loss function if you
yes, you could, but we don't.
But you don't.
We'll get to that in a minute. Okay? One thing here that is important, and I mean maybe this is a remark that's a little bit technical, but it's the importance for a problem like this to do probabilistic forecasting. When you do images, you want to have one image. But here, you really want to have the ensemble of forecasts. Think weather prediction. You really want to know what is the probability for tomorrow to rain. That's one thing. But you also don't want to do regression on the conditional mean. Let me explain that. If you take these forecasts and you average them, then what you get are these images. This is the conditional mean of the forecast of these probabilistic forecasts. So they are correct, but they are just very low in information because you have averaged over all the features that were in the probabilistic forecast. Okay, it's a little bit like if the weather tomorrow could be rainy or sunny, or you want to know what is the probability of each of these events. You don't want to make a prediction which is the average of all possible weather. That would be completely unuseful. Okay? So that's one thing. This is the same thing, to emphasize again without information. This is the same task where you go from low resolution. And there you see that the input data, not at the level of training, at the level of testing, contains a spectrum that's truncated because there is no information besides this. But then when you do the forecast, you actually, it builds up the scale that we're missing, which is, again, is just showing that here you can benchmark. It's pretty remarkable what these networks do. Here's an application for movies. And this movie is actually by nowadays Sora and this movie gen. But this is done a little bit differently. You can, if you have a forecaster, do a rollout. Given the weather today, predict the weather tomorrow. Given your prediction of the weather tomorrow, predict the weather the next day, and then you can roll out. Here's an application where you can do that. You can learn with movies to learn the next frame. You give you one or few frames, and then you train a network that will do a probabilistic forecast of the next frame. Then you take that next frame and you predict what is the next one, and you do rollout. So that's a way to actually create movies. Okay? So these are movies. So this is the original and this is the generated movie that are done exactly in that way. Right? What is sort of remarkable is that this is another picture of this. It's again probabilistic forecasting. So what you see here is, and again this is on testing set. This is what you give after having trained your network, you give it the beginning of a movie, and then you say, give me the end, like predict the movie. And then you can do it many times because these forecasts are probabilistic. So what you see here are different, continuation of the movie. So these movies start with a few frames that are the same, and then one is the true one in the testing set, the other one are the generated one. Okay? And these results are remarkable in the following way, and this is not about, I think that this is done here by using encoding, decoding, but what is remarkable is that the neural network learns to do something that looks reasonable, in the sense that these movies are little blocks that are moving around, and they sort of respect physics. They don't change shape, they don't change color, and they only start moving when another block is hitting them. That's quite remarkable because nothing of this is put in the architecture. It's just learned from scratch. Okay, that's okay. Now, if I still have a couple of minutes, like five. Okay, so I want to switch gear a little bit, and I'm going to go briefly on this because I'm talking to mathematician, applied mathematician, which is that I told you at the beginning that these methods could potentially be useful for sampling. Sampling is Monte Carlo sampling in my mind, and that's something which is usually used in statistical mechanics, Bayesian inference and certainty quantification. The problem that you are facing here is different from the problem that we have been given so far, because when you want to do sampling in statistical mechanics, typically what you are given is some structural information about your target measure, but no samples. The whole task is to actually generate samples. Okay? That makes things much more complicated because at the beginning of the training, you have no samples to actually pair. It's kind of a bit of a chicken egg problem where you need to generate these samples. Okay, so I want to discuss a little bit these tasks, right? And what I want to emphasize, and I will end up with that, is that these are problem with model with no data initially, as opposed to data with no model, which is like images, which is a challenge, but it's also a blessing. And I want to explain that a little bit. So why is it a challenge? For the reason I just said, you have no data at the beginning. Why is it a blessing? Is because if you have a model, you can validate your data, which means that you can a priori reject data that is wrong and keep the data that is right. Okay, so you can create infinitely many data. These days, it becomes actually crucial to try to do that because as generative model becomes more prevalent, not only image generation, but large language model, they are trained on the internet. But they are dumping back on the internet what they are generating. So at some point, they start to train themselves on themselves. And you can do simple experiments that show that this process is very unstable. It goes into noise. Okay? If you have a way to validate the data, that doesn't happen. Okay? And so, you can do that, and, maybe I will go quickly because I want to, that you can do this, so you can learn transport to help Monte Carlo. Okay? And it's essentially, there are many methods by which you can do that. I want to go to my last slides, but there are ways by which you can, at the end of the day, do some form of active learning where you need typically a warm start, where you have a little bit of data, you use it to train a flow, and then you use this flow to generate more data, and you use this data to improve on the flow, and then you keep going. And these methods, for what we can tell in the application that we have, seem promising. Okay, they help. And this is a few examples that I had with that. But I want to end up for the last couple of minutes into addressing kind of the big elephant in the room that we have not addressed so far, which is that we have worked here, in this, as I say, suspension of disbelief, which is that we are assuming that these neural networks are actually doing the task that they are supposed to do. That is, I know that for the young generation, it might be a given, but for people that have been in the business of scientific computing for a bit longer, like myself, it looks like magic because there is this thing which is this curse of dimensionality, which was we were taught, there's a coined term by Bellman that essentially says if you want to do calculation in high dimension, you should forget about it. Why? is because if you're on a grid space in high dimension, you can't do it. Okay? And 15 years ago, if I had started this talk saying I'm going to learn this velocity field, people would have left the room immediately saying he's a lunatic because it's impossible to do. Like there's no way we could do that in high dimension. And so, but nowadays we can do it. And these are also examples, and this just got the Nobel Prize, and it's based on work that was actually done here by Baker's group. These are also inference in very high dimension. Learning how to put the next stone on the game of Go is a pretty high dimensional question. So why is it not subject to this curse of dimensionality? So there's many works, including things on by myself and the group, that try to answer this question. It's a very interesting question to ask, which is what is in the structure of the data or in the performance of the neural network that makes that we can actually bypass this. Okay? And this is my last slide, if you allow me. There is a need to understand this because machine learning is performing amazing feats, but in a way which is not really sustainable. And the reason it's not sustainable is that it's too costly. Okay, and these graphs maybe try to explain that. They are dated by now, but let me just show them to you. So there's two graphs here. This is a measure of the improvement in performance in the neural network as you increase the data. And this is a linear scale, and this is logarithmic scale. So this is actually saying that by increasing, the data increase exponentially, you get at best a linear increase in performance. That's not really good news. That means that you really should focus on problem where you can generate new data, because otherwise you'll get stuck. If you have a problem where the data is fixed, that you're going to reach a plateau. This graph this is no logarithmic, and this is linear. This is the amount of compute that is necessary to train this neural network. Okay? And this is the beginning, AlexNet. This is like the beginning is not so long. And this is like, and the graph would continue. This is an exponential increase in compute that outpaces Moore's law. So it's really like dramatic. Like you really need to put an enormous amount of compute. Like, and these are, I'm just showing you AlphaGo 0, but like if you Chat GPT, GPT-4, all of these things requires enormous amount of compute and, in fact, enormous amount of money, because the consumption of just turning these GPUs is enormous. Okay, and so what that means, and this is really I'm going to leave you with, is that we need to be able to do better than this. By the way, this figure before I go on is my own figure, like with the result of Seinin Che. That show that in the current state of affairs, you need to use big networks. Because if you don't use big networks and you train, these to generate images, what you get is that you get something which is actually not so great. But eventually, if your network has 75 million parameters, then you can train it to give you images that are reasonable. Interestingly, you see that even with the small, you get something which is remnant of the truth, which is this idea that they do generalize. But if you want to make them generalize the right way, you really need to get very high amount of net. And we want to go past that. And what I want to leave you with is that I think that this is a challenge and opportunity for mathematicians, because it says we need theory. And not only we need theory, but we also need to maybe test these models in instances in which, for AI problem where you have models but no prior data. Of course, it's not a dichotomy, black and white, but clearly incorporating some information about models or structures, the fact that we know that fluids are governed by Navier-Stokes equation, don't try to learn that. This information is useful. It should be incorporated. That's probably a way to go around this and to really exploit fully the power of these new tools without running out of energy or gas, because we need to run GPUs for so long. Okay? Okay, that's all I had for you today. Thank you.
Thank you, Eric. We have time for a couple of quick questions.
So you're asking how is it done in practice?
Well, so you generate those predictions, so rain is sunny, so which one is more likely?
So when you have a probabilistic model like this, right, you can generate weather and then you can measure, you can bin. So there's a process at the end which has to be done computationally. You can use your generative model to generate all the ensemble that you care about, and it's pretty fast. And then on this ensemble, you can measure the probability. Will it be raining? Will it be sunny? Will it be this? Will it be that? So that's the way you would do it. Okay? The way you do it, and for example, so this is slightly different, but Google has a tool, it's called GraphCast, which they've trained on data from ECMWF. So 40 years of data that it's reanalyzed data. So it's data that has been created by GCM, etc. So they've used that, and then they've created this GraphCast, and then with that you can start to make prediction. It's not done this way. It's done more the traditional way, where you randomize initial data, which is a bit in principle, but there is a way to do it more principled way. If you have a generative model that is quick, what is costly here, maybe I should answer that, is the training. The evaluation of these things is actually not that costly, right? Once you have a generative model, it goes fast. Like ChatGPT, it costs a fortune and months of training, but when you use it, you can put a prompt and you get an answer fairly quickly. It's the same thing here. Like once you have trained it, you can generate many weathers and then do analysis. Or to do it systematically, I don't know, but maybe there's a way.
It was the most wonderful talk. Thank you so much.
Thank you.
I want to ask about your very last point, which is cases where you have a model but no data. And understand your chicken and egg perhaps perspective or a different angle on that, where you have data, but you want but no model, but you want to have a machine learning type of approach which builds a model from those data, right, and thereby achieves learning something like a Navier-Stokes equivalent. You see what I mean? So
right.
So my question is, compared to like a generic forecasting model or a generic transformer model, do these diffusion-based approaches sort of implicitly give us some sort of a model structure for the forecasting because they're actually ODEs, or is there a way to get that in with this perspective as opposed to, again, a general forecasting or general?
No, for that specific task, which is to learn equation from data.
Well, I just want to get good forecasts, but exploit the fact that there's probably some models somewhere.
So then you need, maybe these tools can be combined with things that are done here by, in the group of Professor Kutz, for example, where you can, maybe try to use that to then validate or build the model where you learn what are the terms in the equation, and do that maybe by inputting some amount of physics that tells you in this PDE, I know that I need to have term of this type and not term of that type. All of these things are really still a little bit in the infancy. So there's many things that, many problems that we can now envision doing, including that. I have kind of presented this a little bit as a dichotomy, model, no data, data, no model. But of course, the truth is in the middle, there's a bit of both. And the challenge now is how to manage to exploit these new tools to actually, do new things. And it's a really, I think we are living wonderful times. Because there is this possibility, dangerous time at the same time. But
I'm super impressed with the preservation of that spectrum, because one of the things that happens in a lot of these neural networks with RMSE, they shave off the high frequency stuff, right?
Yeah.
There's a spectral bias that happens. Do you think this is just preserved because of your diffusion model itself, or the UNet? What's actually getting that tail correctly? That's
okay, so I need to maybe make, answer them, which is that if you do rollout, then unless you put some structure, it will go to hell.
So then it will.
Then it will go to hell,
okay.
right? But I believe, just to answer, but this is, like many things, it would be nice to be able to prove it and to find models that prove it. I do believe that the reason why we preserve well the spectrum is precisely because it is probabilistic. And in fact, it's not very difficult to explain. I don't have this figure, but you know, I think you will understand that quickly. If you don't do a probabilistic forecasting, but you do, for example, conditional mean, and you were to calculate the spectrum of this, you'd get something that you can see what part will it cut, the high frequency, sort of by definition, because you will average. And so the probabilistic nature, the fact that you're using, is not necessarily that it's a diffusion versus an ODE, but it is that the framework is such that you do it as generative modeling, where what you do is that you're generating ensemble of solution, I think is key in example of this type. If you try to do it by regression, then you get the conditional mean, and the information of that is very limited.
So I'm going to propose we move the rest of the questions offline. So let's thank Eric again.
Thank you.